Okay, so welcome back. We will start again with Sonia Boulal, that comes from Institut Denis Poisson in Orléans, and she will talk about conditional marked Galton-Watson trees.
Okay, so good afternoon, everyone. Thank you all the organizers for the invitation and to give me the opportunity to talk about my work. So today I'm going to talk about conditional marked Galton-Watson trees. It's a work in collaboration with my two supervisors, Romain and Pierre. So I'm beginning no. Oh, it's not working. In the end. Okay. So I begin with the Galton-Watson process. So I'm going to introduce all the notation, and we continue with the conditioning during all the year. And after, I will present you the set of descriptors and the mark functions that permit to me to have the marked Galton-Watson trees. And I will finish with the conditioning with the marked trees and also the results that I can obtain. So usually when we talk about Galton-Watson process, we consider an offspring distribution identified by P that corresponding to the fact that all the individuals in my tree have the same reproduction law P and independently of each other. So if I denote by xin the number of children of the individual I at generation n, we have that xin equals k with probability pk. I add some properties on my offspring distribution P. I want to have that 0 plus P1 is less than 1 because I don't want to have a tree with one branch and at a certain time it's finite. So that's why I add this property. And I need to have that P as a moment from the two. It's just the technical proposition. Okay. And I denote by mu the mean number of children per individual. So when we talk about Galton-Watson process, usually we are interested by the total number of individuals at a certain generation, and I denote it by Zn, and I have the indication case that if I sum all the children of the individual at generation n, I obtain the population of the n plus 1 generation. So now we have that if at a certain time it exists n such as Zn equals 0, I have an extension of my population, and we have some case depending on number. Indeed, if I denote epsilon the probability that I have extension, we have the fact that if the mean number of children per individual is less than 1, we have almost really an extension of the population, and we are in the subcritical case. If the mean number of children per individual is equal to 1, we have also almost certainly an extension of the population, and it's the critical case. And finally, if the mean number of individuals is more than 1, we can have an infinity tree, and it's the subcritical case. So that's it on the Galton-Watson process. And now I can talk about the conditioning. So what is the conditioning? When we do that, we consider a sequence AN such that the probability of AN when it goes to t equals 0. When we look at the sequence, we consider the distribution of my Galton-Watson trees given the event AN, and we want to know what is the distribution convergence when n goes to infinity. And when this limit exists, we say that the conditional distribution depending on an converge to the distribution of a limit tree. So, different conditioning exist. The first one was by Kesten. He considers the sequence an corresponding to the height of the tree equals to n. So in this case, we are almost surely finite because we are in the critical or subcritical case. So we know that the tree is at a certain moment finite, but we condition by the fact that the height of the tree goes to infinity, and finally we obtain a distribution at the limit. So that's the first case. Now we have also the conditioning with an corresponding to the total number of individuals on the tree equals to n. It's a work about by Kennedy, Ginger, and Hoffman. This result was obtained just in the subcritical case. Also, we have an corresponding to the number of leaves equals to n. It's a work by Korean and Korchevsky, and just in the subcritical case also. To obtain the result in the critical case, Rizzolo, Abram, and Delmas introduce a generalization of this conditioning, where the conditioning is the total number of individuals such as the number of children belongs to a certain set A equals to n, and they obtain all the results in the subcritical and critical case. So in this last case, we have that an is equal to the cardinal of the individual u a treaty, such as if I denote by T the number of children of the individual Q, you have T belongs to A. And we want that this cardinal equals to n. Okay? So in this case, if we consider that A is the natural number, we can correspond in this case to the second case. Because we look at all the individual, because KT it's all the natural number. Okay, so I introduced you some notation about my trees, and now I will present you this more precisely. So when we talk about the discrete trees, usually we use the novice notation, because this notation permits to know the lineage of individual just when we read its name. For example, if we look at the individual 221, we know that 22 is one of these ancestors, and 2 and also 0, just when we read its name. Now I didn't by absolute Q the generation of the individual U, and also again KT, it's the number of children of the individual U. So if I consider again this type of conditioning, and I look that A, it's just equals to the singleton 0, because
what is the generation of U? Like, what is the generation of U? What would be that?
The generation of U is the height of the U on my tree. For example, 2 here, it's a generation 2, because the root is generation 0, it's generation 1 and 2. Okay? So if we look at A, it's singleton 0, we have AN, it's just the individual with zero child. And in this case, we can represent that by AN represents the individual with just the leaves of my tree. And we have that. So in this case, we can have a mark, just like I put on my trees. And these marks are deterministic, because if my individual belongs to A, I have a mark, but if he don't belong to my set A, I don't have this mark. So the mark are obtained with probability 1 or 0. And in this case, it's not really particular. So in 2017, Abraham, Boisis and Denis wants to add more randomness on this marking process. And so they introduce the mark function Q. How is it? So I have a function on Q. I know that this is just PK is strictly positive. It's just to have the possibility to have a mark on my tree, because if not, it's not interesting. And I denote by eta u the fact that my individual u has a mark or not. Eta u equals 0 if I don't have a mark, and eta u equals 1 if we have a mark. And all the individual on the tree can have a mark independently of each other, just depend of the number of children of the individual. And we have that eta u equals 1 with probability q QT, and it equals to 0 with probability 1 minus q QT. So now I denote by T stars my tree with marks. M T stars, it's the total number of marks on my trees. And 2 stars is my Galton-Watson tree, reproduction law P and mark function Q. So I know it's a lot of information, so we are doing an example.
So K there is strictly positive.
Yes. Just not have a mark on my leaves, because if I mark just the leaves, I know the results. So I want to know the probability that my Galton-Watson, mark Galton-Watson, it is equal to this marked trees. So I do that by observe what happened in the root. So on the root we have children and a mark with probability P3, P3. After I look at the next generation, we have the individual 1 as 1 child and no marks at probability P1, 1 minus Q1. And then the individual 2 has 2 children and a mark with probability P2, Q2. And next, the individual 3 has no child, no marks with probability P0, 1 minus Q0. And I continue with all the individual, and I obtain this expression. Okay. Now we can observe that I can regroup all the terms in P. So here, and here, because like I said, the mark proceeding just depends on the number of children. So I can say that this probability is the probability that my Galton-Watson without marks is equal to this tree without marks, and after I look at each individual if he has a mark or not. And I multiply by the facts that I observe. Okay. So if I can give you an expression here, I have also a general expression for the probability with tree T random. So how is that? We have that the probability that Galton-Watson tree is equal to market trees. It's the product on all the individual of the tree that the individual has Caillou children and Etaillou mark under the probability P0, where P0 is equal to P0 Caillou. Well, it's the fact that I have a mark, it's equal to Caillou. And P0 Caillou. It's the fact that I don't have a mark, it's equal to Caillou. 1 minus Caillou. Okay. So now we have that, and in 2017, Poisson maths wants to understand the behavior of the tree when they conditioned by AN corresponding to the total number of the marks. So we have that AN is the element M2 stars equals to N. So what happened in this case? In this case, if we look at the critical case, they obtain that the distribution of the Galton-Watson tree, given the number of marks equals to N, converge in distribution to Kesten trees with reproduction low P. Now, on my work, I obtain an extension of this theorem like that. It's not just the distribution of the Galton-Watson trees, but it's the distribution of the mark Galton-Watson given the number of mark equals to N, converge in distribution always to a Kesten tree, but not just a Kesten tree, but a mark Kesten tree. So the question is, what is a mark Kesten tree? So, a mark Kesten tree is a tree with two types of individual. We have the normal individual with original P, and we have the special individual with a Bies law corresponding to P stars K equal to stars multiplied by PK. So the root is special, and at each generation, among the children of the special individual, one of these children is special. So at each generation, we have a special individual. But like we saw, here we can have 0 children because the probability is equal to 0. So thanks to that, my Kesten trees have one infinite branch and a lot of Galton-Watson left on this infinite branch. And in the case where we have mark, just at each for each individual in the Kesten trees, we have the possibility to have a mark with the same proceedings that I explained just before. So we can represent this by this this image. So here we have the infinity branch, and we have a lot of mark Galton-Watson trees of finite size branch on my infinity branch. So if you want to have a mountain image of that, you can correspond this Kesten trees to the matching in Jack and the Beanstalk. It's really infinity. So, okay. So now it's all in the critical case. So we describe all the behavior. But Abraham was observe just the case in the critical case, but not in the subcritical case. So now we are testing about that, and to answer the question, what happened in this subcritical case, I need to introduce you another offspring distribution that I denote by PTT. So PTT depends on P and my mark function Q. And I associate to this offspring distribution the mark function TT. So why I do that? It's because I have a link between the distribution of my mark Galton-Watson guessed with a reproduction guessed by Theta and my original mark Galton-Watson. I will show you that. I want to determine this ratio that permits to have the expression of the probability that my guessed mark Galton-Watson tree is equal to a fixed market. So how I do that? I just write what happened. So when I observe this ratio, it's just the probability that on all the individuals that we have Caillou children, and on the individual with a mark, we have a mark with probability Q TT, and we don't have a mark with probability 1 minus Q theta. We know all the expression, so I can replace it. In green, it's probability Q T, and in the blue, it's the probability Q TT. Okay? So when I replace it in the expression, I obtain this equation. And now in this equation, we can cancel out some elements, because in pink, here we have this expression for all the individual in the tree. Here we can observe it just in the case where we are marked, and here we are not marked. And these two set of individuals are disjoint, so it's okay. We have all the individual, and I can remove it. So now I have just this expression. Okay. So now in orange, we can also observe that we have the expression of my probability that my original Galton-Watson tree is equal to the market tree. So I can also remove this term and all this term here, and obtain this expression. So on this product, we can rewrite that by theta power this sum, and on this sum we observe that we sum off all the number of children of the tree. So we sum all the children. So finally, we obtain the total number of individuals, but we forget the root, because we just count the number of children. So this sum is equal to the cardinal of the tree minus 1. And the sum of 1 is the cardinal of the tree. So it's finally theta power minus 1. So this can replace by that. And here we have CTT on the product of the all the individuals with a mark. So all the number of individuals with a mark, it's M T stars. And we have this expression finally. Okay. So now I'm testing by the conditioning by the mark of the tree. So I want to know the probability that my guessed mark Galton-Watson trees has exactly n marks. So I can write that thanks to this expression, because this probability it's the sum on all the tree with exactly n marks, that my the probability that my tree my mark tree equals to the tree this tree, and I can replace it thanks to this expression. So I do that, and on this expression I can go out this theta because it not depends of T stars. Here, empty star is determinist, it's equal to n. So I can also go out of my sum and I obtain this expression. And like just before, this expression, I know that it's the property that my the number of marks of my original tree is equal to n. So I have this expression. And so now I can have the expression of the law of my my Bies mark Galton-Watson trees given the number of mark equals to n. Because if I write that, this property is equal to this ratio, and this ratio, I know all the expression because I determine here and here all that I want. So I replace by the expression that I obtain. And finally, here we can remove all this term. And here we know that it's my condition law of my original mark Galton-Watson clause. Okay? So all this interest of this Bies law is because I have this proposition that the distribution are the same when I condition by my number of marks. And why I want that? I need that because it's because when we are in the subcritical case, we can show two cases. The first case is among all the theta such as p theta is a probability. It exists a critical theta such that my Bies law is critical. And in this case, thanks to my proposition, I can say that the distribution of my original law given the number of marks equals to n, it's equal to the distribution of my Bies law of my Galton-Watson associated to my Bies law given the number of marks equals to n. But in this case, here we are in the critical case. So thanks to my last theorem, we have that this distribution converges to the description of the Kesten trees associated to the Bies law. And so finally, in this case, we can say that the distribution of my Galton-Watson trees given the number of marks equals to n converge to a Kesten trees, but with a Bies law and a Bies mark function. Okay? So it's my first case. Now, if I have the case, okay, everything is good. I find no theta such as my offspring distribution is critical, so I can find my limit tree. But in the case where we don't have this theta, we want to know what happened. So in this case, I need to add some properties on P. I want that P varying regularly, and I need to have that Q as a limit when n goes to infinity. And in this case, the distribution of my condition tree converge to the distribution of a condensation tree, a mark condensation. So what is a condensation tree? A condensation tree, it's a tree like the Kesten tree with special node and normal node. At each generation, we can have a special node, but it's really particular because the special reproduction of my condensation tree is like that. We have k multiplied by pk if k belongs to A, and the particularity of this tree that it can have a node with an infinity of children, and we have that by probability 1 minus mu. So in this case, we have that, okay, like my Kesten tree, the root is special, and among all the children of my root, we have one special node at each generation like that. So we have a special branch, but at a certain time, we have an individual can have an infinity of children. And at the moment that my individual has an infinity of children, all the individuals have the same reproduction node. It's the original reproduction node. We don't have special node after the case where we have an infinity of children. And we can represent that by this picture. So my special branch, and we have a node with infinity of children, and here it's just a Mark Galton-Watson tree, but with each Mark Galton-Watson trees are finite size. Okay. So in this case, my condensation tree is infinitely large because we have this condensation phenomenon, and so it's really, really infinitely large. But it's not just infinitely large, it's also infinity-8 like the Kesten trees, because if I'm here, we have the infinity children, and here I have all my Mark Galton-Watson trees, and if I fix H N, what you want, I can find one of my Mark Galton-Watson trees left on this tree, such that the height of the Mark Galton-Watson tree is higher than H. So we can see like this tree like the pyramid phenomenon, because we are infinitely large, but we also infinity-8, so we can have a lot of mountain if you want. So if you want to have several image like my Kesten trees, it's not the perfect image, but I can propose you the parcel pin, because the parcel pin we have a big tronc, and after we have a lot of leaves at the end. But okay, it's leaves, it's finite, but you can imagine that it's not finite, and it's like that. Okay. So let's do a summary of all these results. If I am in the general case, so it exists details such as PTT is critical, I converge to a Kesten trees, a Mark Kesten trees with Debs law and Debs mark function. If this detail doesn't exist, I converge to condensation trees. Okay. So now there is some particularity, because thanks to this result, I can obtain this results, just the same results like Abraham, Boisson, and Denis. It's a distribution of the Galton-Watson tree given the number of marks, and thanks to my preceding result, I can obtain this one. Okay. Now, to obtain all these results in the generic case, it's okay, but in the subcritical non-generic case, we need to add some properties on P. And I'm not happy to that. So I conjecture that if my radius convergence of this function is equal to 1, I can obtain also convergence to condensation, marked condensation trees. In my case, when P is varying regularly, we have this radius of convergence equals 1, it's okay. And if I say, okay, it works, not for the moment, but if it works, I can add the following corollary. It's like that. If the radius of convergence it's another value, not equals to 1, my Galton-Watson trees converge to condensation trees with Bies law and mark function, Bies mark function depending to the radius of convergence of the generative function. And I can obtain the same result like the one of Abraham Moses and Debs. Okay, so if I accept that, I have that in any case. And it's my following work to find this result. So, okay, thank you very much.
Thank you. Any question? Yes.
I am confused about some simple thing, but how do you, how does your marked tree converge to the distribution to a condensation tree if any marked tree actually has finite even nodes at any? Like, how do you define? Perhaps I don't understand convergence to distribution for that.
Okay, so if I understand well, how my the distribution of my tree can converge to condensation trees thanks to obtain the phenomenon of condensation. It's like that, the question or not?
Yeah, I think, I mean, and correct me if I'm wrong, but any given marked tree only has finitely many children, right? So when you say it converges to a law where you can have infinitely many children,
it's because thanks to the topology that I use, when I observe the distribution convergence, I look at the tree of this form. Yeah. I have this set of tree that on a fixed tree, I have a tree T prime on x, okay? So I print this set, and this set I graph on my tree T, some tree T prime, it's all marked tree, okay? On x, such that the number of children on the left tree it's more than k, and the tree that I graphed on my finite tree T can be infinity. So that's why I can have the phenomenon of infinity, because after we look that okay, it can happen, but at the beginning, T is finite, but thanks to all the trees that I graphed, it's okay. We can have infinity tree. Okay.
Questions? Maybe I have one. It's more a curiosity. So in your framework, when you have your events PM, can you also deal with the case of condition to survival? Can you deal with condition in this sense?
So in the case where for example, I'm the supercritical case, and so I think we can, but I'm not sure that it's interesting to have the result. I think that we obtain the description for tree like my original tree, not a special tree that we can observe, because the particularity is that, okay, normally I can have an infinity tree because I'm in the subcritical or critical case, and finally we obtain a tree that can't extend. So that's why it's interesting, I think.
I was thinking a little bit to the previous talk, in particular to the case of a uniform spanning tree on the graph. You know that in that case,
Yeah.
But
I don't know.
Other questions? Okay, if not, let's thank again the speaker. And we have a short break, 20 minutes again, and we will resume at 4 p.m.